Okay, my friends, so let's go back to the 0 to 1 hour part of this study. Our hypotheses are those. We either don't or do have a negative effect on lung function. Now, because of the p-value that we got, less than 5%, very small, we choose probabilistically to believe the research hypothesis. It appears that secondhand smoke has a negative effect on lung function. But could we be wrong? And the answer is yes. The bigger question is, how could we have been wrong? Okay, now, I'm not saying we are wrong. There's always a potential for being wrong, and here's why. That right there, my dear friends, is going to be the null hypothesis sampling distribution, non-reduced lung function parameters. Okay, again, I'm not a biologist, so I don't exactly know what they're measuring, but whatever they are measuring, it follows a distribution. That's what it is. Assuming that to the right side of the curve is higher and to the left side of the curve is lower, that means that reduced lung function parameters are going to be to the left on average of the blue curve. Yes, they do overlap, as you can kind of see here in the middle, but that's in the same way that 11-year-olds and 12-year-olds heights and weights overlap. The tallest 11-year-olds are going to be taller or as tall as the shortest 12-year-olds. So you've got some overlap, but the majority of the curves are separate. Now, in this study, where did our data land? Well, it landed somewhere around there. And why did we choose to believe the research hypothesis? We believe that because we set up our region of 5%. The other part of that curve is the 95%. And we told ourselves, if we escape the 95% confidence interval, we will land in the 5%, used to be called the rejection region way back in the day, but what it means is you traditionally reject the null hypothesis, and more sensibly, you choose to believe the research. Because it's more likely, as we said before, that asterisk is on the reduced curve instead of the non-reduced curve. But there is still a chance that asterisk belongs on the blue curve. It's a small chance, but there's still a chance. So let's formalize this. Okay. Ways to be wrong with the conclusion on a hypothesis test. So the test itself is going to run. You're going to get a result. You're going to make a conclusion based on the p-value. But realize this is all based on probability. There's always a chance you could be wrong. So if you get a small p-value, the common and most correct response is something changed. That's absolutely the most common and most correct response, because it's too hard to believe you're on the null hypothesis curve. That means you're probably on a different curve, which means you should believe the hypothesis for the different curve, the alternative hypothesis. Beautiful. But if it hasn't, but you concluded that it did, as you should have, you made what's called a type 1 error. Let me go into that in more detail right here. Okay, my friends, type 1 error on a hypothesis test. This means that you got a small p-value, concluded that something changed, but it didn't. I'm not saying that small p-values always imply errors. Trust me, I'm not saying that at all. What I'm saying is small p-values make us reject the null hypothesis, accept the research hypothesis, and sometimes we're wrong. So said a different way, it means we're saying something changed when it actually didn't. We're saying the status quo has shifted when it actually didn't. In that way, it's very similar to what you're studying in your project this week, which is a false positive on a drug or a disease test. Meaning, you took a test to see if you have something in your system. The status quo is you don't. But if it comes back positive, that's a false positive. So a type 1 error and a false positive are basically the same idea. Why the language is different, I have no good answer for you there. This is generally more of a medical or judicial kind of phrase, and this is a statistical kind of phrase. Why there's two different languages, I don't know. Apologies. But in statistics, if we are operating at 95% confidence on these tests, which we've pretty much done all term, then the chance of a type 1 error is going to be 5%. And the reason it's going to be 5% is we are going to reject the null hypothesis, accept the research hypothesis, if we escape the 95% confidence interval. The only way we can be wrong is if we escape it, say that we're not in the interval anymore, when we actually should have been. And that's only going to happen 5% of the time. So, it could very well be that we just got randomly deviant data. Maybe lung function parameters are not impacted at all with secondhand smoke. Maybe we just got incredibly deviant data that sent us into the low end of that curve. It's possible. As a matter of fact, my man Doc Brown had something to say about it in Back to the Future too.
Next Saturday night, we're sending you back to the future. Let's set your destination time. This is the exact time you left. Let's send you back at exactly the same time.
You're not gonna believe this. We gotta go back to 1955.
I don't believe it.
That's right, Doc. November 12th, 1955.
Unbelievable that old Biff could have chosen that particular date. It could mean that that point in time inherently contains some sort of cosmic significance, almost as if it were the temporal junction point for the entire space-time continuum. On the other hand, it could just be an amazing coincidence.
And I think Doc nails what a type 1 error or a false positive is very, very well. It's a chance of an amazing coincidence. It's the chance that we got data that makes it look like something happened interesting, but really nothing happened interesting. Now, that's not to say that every time you get a small p-value, it's going to be a type 1 error. Not saying that at all. Just that it potentially could happen. If you get a small p-value, reject the null, believe the research. Cool. What if you get a big p-value? Could you be wrong that way too? Let's look at that next.